This is the BME 271 lecture on thermography and light sensors. So let's first talk about some motivation for discussing thermography. So all of the temperature sensors that we have so far talked about have required direct contact with tissue. And this is because what they actually measure is the temperature of the sensor itself, rather than the temperature of the tissue. So heat has to be transferred, in order to make a measurement, heat has to be transferred from the tissue to the sensor. Okay, now there are two drawbacks for this. One is that it can be a slow process, meaning that which is embodied by the fact that we have a relatively large time constant tau with which the heat transfers from the tissue into the sensor. The other potential issue is that you have the potential for unsanitary conditions. So it's potentially unsanitary to have to bring a sensor directly into contact with tissue. And it's also then potentially invasive if you need to get a more internal measurement. And so, and in addition to that, patient compliance can be an issue. So as an alternative, thermography is a method for making images of temperature that are based on the emitted radiation, and specifically emitted radiation in the infrared range. So a hot object will emit infrared radiation, and instead of putting something into contact with that tissue, we instead actually rely on the fact that it's emitting photons that we can have a detector sitting off from the tissue to detect. Okay, so as we said, hot sources emit heat as infrared radiation. And the amount of infrared power emitted from a hot surface per unit area per unit wavelength is given by Planck's law. Which I will write here below. So Planck's law says that the infrared power, which is measured, which is called W sub lambda of T, so it's a function of both the wavelength and the temperature, is equal to the emissivity, that's this epsilon term, which is also wavelength dependent in general, times a constant C1, which is given below, divided by the wavelength raised to the fifth power times e to this constant C2, which is also given below, divided by lambda, the wavelength, times T, the temperature in Kelvin, minus 1. So this is Planck's law, and it tells you about the power density, essentially, per unit wavelength. So I've given all the parameters here below, these fixed constants C1 and C2. T, again, is the temperature in Kelvin, and epsilon is what's called the emissivity. And it happens, it's very convenient fact, that emissivity is about 1 for skin, regardless of the wavelength. And we can use Planck's law to make an image of temperature by measuring the magnitude of the emitted radiation from each location or pixel in a thermography image, which is a measurement directly then of W sub lambda of T, and use the W sub lambda of T equation to get the temperature back. So with these measurements, there are at least two ways to do this. One of them is to measure W sub lambda over a large lambda range, and then find the lambda at which W sub lambda is maximized, and then we can use this fixed relationship that the temperature is equal to 2898 divided by the lambda at which the W sub lambda of t maximum occurs. So again, this is the lambda at the peak W sub lambda. And so if you measure W sub lambda over this large lambda range, you're going to get a measurement that's going to look something like this. We'll show it on the next page. It's going to look something like this as a function of lambda. And so what you do is you figure out, once you made that measurement, then you see, well, where on this curve is the peak lambda. So that would be right about here, and that gives you the lambda sub m. Okay? The other approach is to fix the lambda of your measurement, fix the wavelength of your measurement. In other words, measure W sub lambda only at one wavelength, and then invert W sub lambda to get the temperature back. This turns out to have somewhat limited range, as we'll see on the next slide, because W sub lambda is not monotonic. Let's see, in temperature. It's not monotonic. And so it's possible that you will get the same value of lambda at two different temperatures, or the same value of W sub lambda at two different temperatures, but it does involve simpler hardware since you only have to make one measurement at one wavelength. So here's an illustration of the W sub lambda of t function, or the W sub t of lambda function. So here we're plotting this function as a function primarily of wavelength for a fixed temperature. So we've got it plotted, we've got W plotted across a range of wavelengths at four different temperatures. 80 degrees here is the lowest curve, 105 degrees, 150 degrees, and 300 degrees Fahrenheit as the highest curve. And you can see that essentially it humps and then it goes back down. Now, what we would do with the first measurement approach is that, again, we would measure this function across across a large set of wavelengths, and then we would find the point at which it peaks, and then we say that that is lambda sub m, right? So if you had a true temperature of 300 degrees, then this would be your lambda sub m, right? That would occur right there, and you would look that up, and that would be about maybe 7.5 microns. And then you would use that T equals 2898 over lambda sub m relationship to get the true temperature. Okay. On the other hand, now the second approach then, of course, is to just fix your wavelength. So that's what I've plotted on the right-hand side, is the W sub lambda of t, where I've fixed lambda, the wavelength, and then plotting the function as a function of time, or sorry, as a function of temperature. And so here I've got degrees Fahrenheit on the x-axis, and I've restricted the axis somewhat between 90 and 110 degrees. And over this range, the infrared power W sub lambda is a relatively linear function of the temperature, and so we can use this relationship to get back what the temperature was from this relationship. But of course, if we go far outside this range, it's possible that the temperature it's possible to get for this curve to go back down again. So that's because you can have, for one temperature, as you see from the left-hand side, you might have a spectrum that looks like this, whereas for another curve you have a spectrum, for a completely different temperature that's very far away from that temperature, you have a curve like that, right? And so you can get the same, as you can see here, you can get the same W sub lambda of t for two very different temperatures. And so it's not, you have to restrict the range you're looking at in order to get a unique solution given a certain measurement at one wavelength. Okay, so what is thermography good for? What has it actually been used for in practice? One is as a non-invasive thermometer. So essentially that would be like a 1-pixel image, right? You'd have a single sensor, a single infrared sensor, and then use that one point as an non-invasive thermometer where you just essentially bring it close to the tissue, but you don't have to directly touch it. And then maybe you put a cone around it so that all the infrared energy is only coming from the tissue itself. Another application that has been looked at fairly extensively, but actually isn't really used in practice, there's a lot of excitement about it, but it has not panned out really, was detection of breast cancer. It's actually it was a very controversial thing. The idea being that during angiogenesis you have temperature rises, right? So you'd have and the idea would be that you would leverage the feature of thermographies that it can get very good temporal resolution to detect small changes in temperature that would be due to increased vascularization in tumors, even in deep tumors. But it turns out that scatter is a big problem with that. Mammograms also still detect tumors earlier since they see them prior to angiogenesis, which is the point at which the tumor becomes malignant after all. So you really want to detect the tumor before it becomes malignant, and so then before the angiogenesis occurs, and then therefore before you can actually detect it with thermography. So the FDA does not actually approve thermography for breast cancer screening, even though you can. I think that there are some clinics that offer it. What I'm showing here is an image from a FLIR device, right, showing a snake coiled around somebody's hand. You can see obviously that the hand is quite warm, around 32 degrees, approaching body temperature, and the snake, of course, is much colder. One other application that we use these devices for in MR is to image distribution of heat in phantoms when we're trying to figure out whether a new RF coil or a new hardware design inside the bore will cause RF heating in tissue. So you can build a body mimicking phantom with similar electrical properties to the tissue at those RF frequencies at which the scanner operates. And then you can use a FLIR camera or something like this that is essentially, implementing thermography to detect whether or not you are heating that phantom up beyond safe levels. So let's move on to light sensors now. So first we'll introduce a metric by which we often compare light sensors, which is called detectivity. And that is this D star parameter. D star, let me find an asterisk here. So it's called detectivity, D star. It's also known as specific detectivity. Okay, and it's given by this equation. D star is equal to square root of A times delta F divided by NEP. So there are three variables in here. The first is A, and that is the area of the detector. Delta F is the frequency bandwidth over which you're measuring the light, or 1 over the is the frequency bandwidth, or 1 over the wavelength. And NEP is the noise equivalent power. So that is the power required to get an SNR of 1 for a given sensor. And so that's going to be sensor dependent. Okay? So it turns out that this metric is normalized by the detector's area, even though it's multiplied by the root of the area. It turns out that it's actually normalized overall if you were to plug in all the definitions of these things. Since the number of photons per unit area decreases as distance from the source increases. So therefore it's possible to make any detector more sensitive just by increasing its surface area, the surface area of the detector. And we can appreciate the fact that the photons per unit area decreases as distance increases by thinking about a source, which I represent here as a circle, that is emitting photons, which I represent here as these little arrows. And depending on your distance away from away from the source, if you draw like a shell, for example, let's say we draw a shell at two different distances. Let's say we draw a shell here and then a shell further away here. The density along the area of the red shell is going to be much higher, right? The photon density is going to be higher for any given unit area on the red shell than it will be on the black shell, since the photons, there's finite photons and they're spreading out. Okay? So recall from earlier that hot things radiate infrared radiation. And in general, then, we can use temperature changes in thermal sensors, right? So not actual light sensors necessarily, but thermal sensors due to incident light to measure that light. So incident light on any given thermal sensor will change its temperature, and we can use that to measure the light. So, and that's the first kind of light sensor that we're going to talk about, is these thermal light sensors. And so again, such detectors are called thermal light detectors, since they are based on temperature changes in the device due to incident light. And there are three types. One we've already talked about, which is thermopiles in the last lecture. Oops. I should say thermopiles. The second is bolometers. And these are devices whose resistance, delta R, the resistance changes with incident light. And the third kind is pyroelectric. And we'll talk more in particular about pyroelectric sensors. Electric. So thermal light sensors dependent on the pyroelectric effect is what we'll talk about next. So this effect refers to temporary voltages that are produced across a given crystal of a certain material when it's heated or cooled. And that means that currents only appear when temperature changes, when temperature of the crystal changes. So electric currents only appear on the crystal when temperature changes, and those currents are proportional to that size of the change in temperature. Okay, so if the currents are only appearing when temperature changes, that means that if we have a fixed constant DC light, or a fixed constant light intensity, or a DC light intensity, then we're going to need something that we call a chopper to be able to make a continuous measurement of it. Okay, so I'll illustrate that here. So let's say we have a light source, which I'll represent as a candle here. So that's our source. And then we have our crystal here, our sensor crystal. I'm trying to draw a crystal there, like a diamond kind of shape. So when we first turn on the source, we're going to get some voltage change across the sensor crystal, but then it will go away and we won't be able to see any signal after that. So what we have to do is introduce a chopper. And so this is essentially like an opaque wall that we move up and down between the source and the crystal, so that it's constantly changing. The temperature on the crystal is constantly changing. And so then we get electric current arising on the crystal whenever the chopper is pulled away or moved back, so that the sensor crystal changes temperature at that point. And that is how we can make continuous measurements of the light source. And it turns out that for the other thermal light detector types, such as the thermopiles and the bolometers, we also need choppers to separate signal from ambient temperature. So for a slightly different reason, not because we won't get any signal when we have, not because we won't get any signal when we have a constant exposure to the source, but because we won't be able to separate it. We won't be able to essentially filter the filter out the signal that we're getting from ambient temperature from the signal that we're getting from the source. But if we add a chopper, then if we have a chopper between the source and the detector, then the signal components corresponding to the source will have a higher frequency than the ambient temperature signal component. So you can imagine that we can use a high pass filter to get at the signal components due to the light source. So the response, the advantage to these thermal light detectors in general is that their response is relatively independent of wavelength of light, right? So you can get a wide band measurement. There are disadvantages. There are a couple disadvantages to them. One is that they are slow, right? Because for again the same reason that it takes a while for them to heat up, right, in response to exposure to a light source. And they can also have low sensitivity. Which again would be quantified, they would have a relatively low value of their specific detectivity. So in contrast to thermal light detectors, photon detectors are the other type, and they directly convert photons striking a material into changes in current and voltage, or into changes in conductance or resistance equivalently. And there are several types. We're going to talk only about one of them here. And the first major type is semiconductors, and this is certainly going to be the most common that you're going to find. One type of semiconductor one is photodiodes, and we're going to talk in more detail about that in the next slides. Then other types include PIN photodiodes, which work a bit differently. PN junctions. PN junctions. And transistors, that you can essentially expose the gate of the transistor to incoming photons. And again, it's the photodiodes that we're going to talk about in detail on the subsequent slides. Other types are photoconductive cells, right, like solar kind of cells, and photomultipliers. Okay, so getting into more detail into photodiodes. In photodiodes, we have photons that collide with electrons in the diode. And if those photons have sufficient energy, then the result of that collision will be that a whole electron pair will be produced, and that pair will be swept in opposite directions across the junction by the intrinsic electric field built into the junction that we get when we bring the two materials that make up the diode together. Then we get this intrinsic electric field across the junction. It's built in, it's always there. And we get, when they're swept across that junction, of course, because they're moving, that creates an electric current. And it turns out that it's a reverse current compared to the convention of which way current goes in the diode. And that reverse current will do two things. It will have two characteristics. One is that it will increase linearly with incident radiation, since each incoming photon, since the radiation is proportional to the number of photons, and for each photon that comes in, 1 unit of current is produced. So it's going to be linear with incident radiation. And the other thing is that it's going to be fast. Or it occurs quickly. And it turns out that the response times are on the order of maybe 1 microsecond. So you have a current arising less than 1 microsecond after a photon comes in and hits an electron, generating an electron pair and producing a whole electron pair and producing a reverse current. And here's how we could use a photodiode in a circuit. So here I've drawn a circuit, a simple op-amp circuit, which is just a current to voltage converter, right? So we talked about this kind of a circuit recently when we talked about current to voltage converters, where the diode itself is actually the current source here, and we flip it upside down so that the current so that the current through the diode is going the way we would like it, so we get a positive voltage out. And so then the current through the diode here, right? Note again that this I sub d is referenced opposite the direction that you would normally have current going through it, reference current going through a diode, which would be going from anode to cathode. We are doing the opposite, going cathode to anode. So this current has a linear dependence on the incident light, given by I sub d equals I sub dark. You guys have now seen this. I sub dark plus alpha times the light power. Okay, and this term alpha is what's called the flux responsivity, and that's in units of amps per milliwatt. And so then the light, of course, would have to be in units of milliwatts, so that cancels out, and you just get amps, which are the units of current. And the dark current here is a fixed quantity that is due to primarily other background radiation. So in this current to voltage, in this current to voltage converter circuit, the diode is reverse biased, just meaning that the voltage across it is less than its turn-on voltage, which is usually around 0.7 volts. And here, in fact, specifically, the voltage drop across the diode is exactly 0 volts, right? Since we have it connected to one of the terminals of the op amp, and the other terminal is tied to ground. So then it turns out that we can now draw the voltage current curve for the diode, and as we vary the incident light, this curve is going to move up and down. So the current is going to move up and down the V sub d equals 0 vertical, where V sub d is the voltage across the diode, which is fixed at 0 here. So if we draw this whole curve, you guys have probably seen this before. Note here that I'm now plotting minus I sub d, where I've defined I sub d as being the current by the current direction by the convention as I have it drawn on the previous slide. So this is consistent with the way I've got it drawn. So with no incident light, we'd have some small reverse current, some small offset from 0, from the from the d equals 0 point. We'd have some small offset due to the dark current, and that's for the case with 0 milliwatts. And as we increase the power, let's say arbitrarily in steps of 5 milliwatts, say that we have 5 milliwatts, then we go to 10 milliwatts, we'll get the same step size in current across from the diode, and then maybe 15. So these guys are the incident light, the P sub light. Okay, so it's going to be, what we're doing in that circuit is we're fixing V sub d to 0, so we're moving up and down this vertical with increasing or decreasing light. So some of the advantages of photon detectors are, again, that they are fast, as we said before, and they also have a high detectivity. Which is on the order of maybe about 10 to the 12th. So it's quite high number there. The main disadvantage to them is that they are sensitive to a relatively narrow range of light wavelengths, and that's due to the selected photoconductor, that range of wavelengths that any given device is sensitive to is due to the selected semiconductor band gap energy. So this is the energy required to produce that whole electron pair, right? And it turns out that energy is a function of the energy that any given incoming photon has is a function of its wavelength, and that energy increases with frequency. So So that's why we have this relatively narrow sensitivity, is that it takes a certain energy to knock the electron out and create a electron hole pair, and so that energy is dependent on the wavelength, and that energy will also depend on how the device is built. So let's say we have a given spectrum to which we are sensitive as a function of lambda for a given photodiode. So this would be sort of the sensitivity, or the detectivity, D star, of the photodiode, whereas a thermal detector is going to have a much broader albeit lower, specific detectivity. As we said, they are pretty much lambda independent. So to finish up, let's briefly go over some light sensor applications. So one of the first set of applications is the detection of frequency-specific emissions, frequency or conversely wavelength-specific emissions. So for example, we have infrared detection that we want to do to measure temperature non-invasively. We also have applications in fluorescence or luminescence, luminescence. And then there's optical spectroscopy, such as near-infrared spectroscopy, which is a method that is used for can be used for functional brain imaging, optical functional brain imaging. Nerves. And so I've illustrated those. I've just pulled some images off the internet to illustrate those. So this is an image of a NIRS setup where we have a given optical photon source that then injects photons into the tissue, where they scatter and are attenuated by the tissue depending on its properties, such as oxygenation of blood, and then they come back out and are sensed by detectors. They bounce back out and are sensed by detectors that are placed somewhere near the source. And then on the right here, I've got just a fluorescence image, an example of a fluorescence image, which is often used to image functional aspects of cells, or functional or geometric aspects of cells. And then there's remote sensing as another area of application of light detectors. So in within remote sensing, we have uses in interrupter cells and optical encoders. And also in interferometry. And we'll talk specifically more about optical encoders in the next couple of lectures. Another application that finds lots of uses in biomedical research, in biomedical work, are using light sensors plus light sources as a means of optical isolation, or opto-isolation, which is used to reduce noise and also common mode signals that might arise if we use wires to transmit electrical wires to transmit signals. Bring that down like that. Okay, so for example, I think I talked about this previously in the course, but in MR now, all the receivers, all the RF receivers inside the bores are now going to optical connections to the outside, so that they don't have to send these long transmission lines, essentially, to transmit the signals all the way, 20, 30 feet to get to the room where they're actually digitized. So now they're using optical lines to do that instead, to reduce that noise. And then finally, of course, in fiber optics, light sensors and light and sources are used all the time in fiber optics.